guess I'm ready whenever everyone else is. You guys can hear us online, okay?
Yeah.
Yeah.
Okay. Yeah. So thanks everyone for coming. I gave Jackson quite a task for the summer, especially just a little background. I think it's correct to say you only started learning from 3D this year.
Yeah,
in the spring.
back in October.
Yeah. So I mean, he's done a lot of great work this summer. I'll leave it to him to kind of introduce what he's been working on, everything, but really getting some good insights, getting some new methods set up for us, and yeah, I'll just let you take it away.
Right. Hey everyone, my name is Jackson Asiatico, and kind of like Eli said, I've been working on some CFD methods. So the title of this research is Dynamic Body CFD using Unstructured Overset Grids. So a little bit of introduction about myself. I did get my bachelor's in mechanical engineering from Georgia Southern University. I was under my previous advisor, Dr. Marcel Ely. And this is kind of the first introduction that I kind of had to CFD. It was in my senior year, and some of the projects I was working on was synthetic jet actuators, combustion instabilities, as well as cavity flow for scramjets. Upon graduation, I did think that I wanted to pursue a master's degree in aerospace engineering. So I came down to the University of Central Florida, where I have my current advisor, Dr. Michael Kinzel. And some of the projects that we've been working on is the effects of fluid shear stress on the development of osteoporosis under microgravity. And then, of course, leading into this current presentation about just sort of the entry, descent, and landing of blunt body vehicles. I do plan to continue my PhD, still at the same university under Dr. Kinzel. And over the summer, my NASA mentor, he's been with me for almost 12 weeks now, is Eli Shellbarger. So first, before I get into the outline, I just do want to go over my quick project goals and what everything I've been kind of aiming towards this summer. So the main overarching goal that we try to target was to utilize overset grids for dynamic modeling. So we wanted to compare a previous method that has been in use here at NASA Langley for a while called rigid body motion. So that has been the current standard here that we've been using to model dynamic motion. And then there's this newer method that is kind of more state of the art. It's called overset motion. And I'll talk about exactly what is overset motion a little bit later. So we wanted to demonstrate that overset motion did have the same dynamic prediction capability as rigid body motion. And then a subtask of that is that we also wanted to compare these CFD results to experimental data. This kind of separates, your colorful fluid dynamics from your computational fluid dynamics. So you wanted to kind of ground this data with some real testing data. So the vehicle of choice that we had in mind was the Mars Sample Return or the Mars Sample Return Earth Entry System, or the MSR-EES. And the reason why we chose this vehicle is that because it's been undergoing quite a few dynamic testing within the vertical spin tunnel as well as the transonic dynamics tunnel, which is kind of the baseline for our project here. Now, overall, this CFD and this experimental data serves to aid in the development of the Aero database, like in Ben's presentation that we just had a couple minutes ago. This kind of helps to feed into post-2 trajectory simulations. And I also do want to note real quick that the TBT testing data was not quite available, so it wasn't available on time, unfortunately. And as well, I would also like to mention that the following data that I will show in this presentation doesn't really serve as a means to develop this Aero database itself, but it's kind of a good benchmark test to prove that it can be in the future. So some quick overview of what I'll be going over in the following slides. I will continue with a background on dynamic testing, as well as my general workflow outline for what I've learned over the summer. Then I'll dip into overset methodology, what it is and why we're choosing to use this method, as well as the data of all of it. So the solver setup, data and post-processing, and the comparison of overset and rigid mesh motion. Then I'll try to wrap up everything. I'll talk about any issues that I had, some limitations, as well as my conclusion. And then lastly, I'll follow with what's next for me, where am I going after this? And then the acknowledgement of everyone who has helped along the way. And shortly after that, I'll have some time for some questions. So kind of as a baseline for dynamic testing for experimental uses, there's really two main methods to kind of simulate this dynamic motion of these blunt body vehicles, one of which is the ballistic range. And essentially all this is that you're putting this model into a what is essentially a tank cannon, and you're shooting it down this long corridor, and they have multiple cameras set up where they can take pictures at set intervals. And then from this, you can kind of back out the way the vehicle pitches. So this is a very good way to simulate real flight dynamics. It's essentially flying through from Mach 4.5 and slowing down to Mach 1, which is kind of what we want to target. But the issue with this is that I said, so they're just taking pictures of this. So there's not really a good direct measurement of data. And it takes months and months to actually process all this data to get useful data for all of us. The next case is a force oscillation case. And this is essentially what I mentioned earlier about the TDT. You put this model into some dynamic wind tunnel, in our case, the TDT, and then you rotate this model about a fixed point. So this is a very controlled environment to back out these forces and moments because you know the frequency at which the model is oscillating, and then you can also back up the forces. Now, our current focus here at Langley is kind of to improve these CFD methods. There's already a good background knowledge in the rigid motion for force oscillation, but in terms of actual using overset grids, there's not really a good background for that, and also in the case of ballistic range. And this is kind of mainly because a lot of times for something like ballistic range, it's a 6-stop motion, so a 6 degree of freedom. So you have all the different ways that the vehicle can move. So it's very computationally expensive. So these are the tasks that I kind of outlined here. It's kind of what I would visualize as a typical CFD workflow. So you obviously have your pre-processing stage where you talk about your grid generation and your geometry, various gridding techniques. So in this case, we use pointwise and Helder mesh to generate our grids to discretize the domain. And then we move down to the solver. We use Fun3D, which stands for fully unstructured Navier-Stokes equations in 3 dimensions. This is an unstructured solver, which I'll get into that later. And we run it here locally at the HPC cluster on K. Next, post-processing, we use TechPlot, which is just another software to visualize all of our data. We use various Python scripts to help compile all this data and manipulate it to how we want to analyze the data, which we'll talk about in a second. So to kind of break up more of the pre-processing stage, fortunately, we already had the geometry given to us, so we really didn't have to worry about making sure that it's a watertight geometry. We are using an unstructured mesher with Helder mesh and pointwise. Now, there's 2 things that we were kind of keeping in mind, the rigid body grid and the overset grid. And to kind of define these right now, so the rigid body grid is one single contiguous grid. And some of the issues that you might see with it versus an overset body grid is that you're wasting a lot of grid space within the wake. And then for every new vehicle that you want to simulate or different iterations of a vehicle, you have to generate an entirely new grid. Now, moving over to overset body grid, they do have multiple grids that overlap. And maybe some of the things that you have to keep in mind for this is that you have to have adequate overlapping and adequate sizing between the different grids that you want to look at. So to dive more into overset grid and exactly what it is, I have this diagram right here. This is from Overflow, which is another CFD solver at NASA, which is a structured overset solver. So as you can see in this picture, it might be kind of hard since you guys are a little bit further away. But for everyone online, you can see that there's multiple grids in here. The red structured grid on the right. This is what we call a background domain, and then you have subsequent smaller domains within that domain that kind of serve as a refinement zone. And this really helps with large relative motion between different bodies. And the way that this works is that you're interpolating between the different grids. Now, it's not just enough to take these grids and then just throw them at Fun3D. Fun3D will not know what to do with all these grids, so you need something that's called a grid assembler. And this essentially just recompiles a grid into a format that Fun3D can use. So what we've been using in the past is Sugar++. One of the downsides, obviously, is that it requires a license, so that can be very expensive at some times. Now there are a couple other ones like Pegasus and the main other one that they use for overflow, but Fun3D does not support this. One of the biggest differences is that overflow is a structured solver, whereas we're using an unstructured solver. And then lastly, that gets to the point of this presentation, which we're using Yoga, which Yoga is just a recursive acronym that stands for Yoga is an overset grid assembler. It's developed here at Langley by Cameron Drew Jr., and it is also open source. And one of the biggest things that came with the development of Yoga is that it was one of the first to actually parallelize, this process, which kind of paved the way for things like Sugar++ to develop their own parallelism. Now, in order to kind of get a better understanding of what exactly is rigid body motion versus overset, I have these little just PowerPoint cartoons here. So on the left, you can see the rigid mesh motion, and then on the right is the overset motion. Now, the colors just indicate different grids, which I'll talk about. So the blue represents one grid, and then the red represents another grid. Whereas the yellow that you can see is following that body is just a refinement zone. So it's not exactly its own grid itself. It's just in the area of very dense grid resolution. As you can see on the left, this rigid mesh motion only has one grid, whereas the overset motion has two grids. And then essentially we're prescribing this 30-degree angle of attack in this scenario to both of these bodies. And you can see that the wake zone in the rigid mesh motion is actually leaving, the area where the wake should be, as indicated by the line. But then you move over to the overset motion, and the wake stays within the flow. So this is very, this is what we want. We want to be able to resolve this wake. Now, this is kind of a worst case scenario, quote unquote, simply because traditionally in a rigid mesh motion, you are able to rotate this wake to align with the free stream flow. But this also requires a very case specific grid. So in this scenario, you're oscillating about 0 degrees, but if you want to oscillate at about a different point, you have to make an entirely new grid. Whereas in overset motion, you can rotate it the wake with Yoga, and then you're only rotating the inner grid, that red grid right there. So it really helps you to tighten up this the wake. Yes.
Why can't you just keep that yellow for the rigid body just fixed and then rotate the body within it? Like, why do you have to rotate the yellow with the body?
That's just because, so the way rigid mesh motion works, I guess I kind of skipped over this, is that essentially you're rotating the entire domain. So you can't just keep the body rotating with the wake in one place, which I do have a video in here that maybe can help describe that.
Okay.
So here's some preliminary grids that we use in Pointwise, that we've made in Pointwise. And as you can see, this just utilizes two grids. One is an inner grid and one is a far field grid. And these preliminary grids, it's very coarse. It didn't really have a wake or a shoulder refinement. Now, we did switch over to Held Mesh. It is a lot faster to actually make these grids. One of the problems that we ran into was source refinements, which is essentially in Pointwise, it was kind of hard to make any transformations such as translations or rotations of the actual source refinements. So moving on to our Held Mesh grid, this is just another preliminary grid that we made. You can see that we did add a shoulder refinement to capture the shear layer. This flow is separating off the body, off the shoulder, so you do want to capture that. And then also the wake refinement, which you can't really see in this picture, but it helps you capture the turbulent flow behind the body. And it's very important whenever you're talking about something like a axial force. And then in all of these cases, we did target a Y plus of 1, but which is specific because based off of our turbulence model, we have a RANS model, and typically you do want to target something like a Y plus of 1. So these are our final grids. You can see that there is a little bit of a difference, mainly due to the time constraint. So it's not a true one-to-one comparison, but you can see that the grid points are fairly similar. So you got overset at 9.3 million, and then the rigid grid at 8.2 million. And they are essentially pretty coarse in the actual mesh. So it's not a very high fidelity simulation, but that's not what we were targeting. Now, the biggest thing that you can see the difference between these two is that you're really tightening up the wake inside the overset motion, and you're able to move these grid points from the wake and then move it to the front of the body in order to help capture, things like your bow shock, which is not something that you can do in that rigid mesh motion unless you add more grid points to the front. And here's just a blown up image of your body. You can kind of see that the grid spacing between the two meshes are very similar. So I will go back to the last slide just to kind of give you an idea of what this image is showing. But essentially, I'm just highlighting the Mach number limited to the refinement zone where there's a very dense mesh. So if I go back real quick, you can see that the grid surrounding the body is very dense. And then as I go to the next slide, that's just what is portraying. So this kind of helps to highlight, exactly where is the wake in relation to this high density region. So in the overset motion, like I said, you can tighten up this wake a lot, so where you're not having all this quote unquote useless grid space in the wake, and then you can kind of move all that grid points to the front to where you can capture this bow shock. So here's some animations of what your rigid mesh motion would look like. And to Liam, to answer your question, as you can see on the left picture, your entire domain is rotating. So that's just the way that rigid mesh motion works. Whereas in overset motion, you can prescribe the motion to a single grid. I hope that answered your question. And then, as you can see in this one, so your rigid mesh motion is still not utilizing the full span of the wake. And with the overset motion, you can kind of tighten that up around it. Now onto the solver. So we did run a couple different cases in order to help set up for the dynamic motion. So on the left, I'll just start with the rigid motion. We initialized the solution with a static solution in order to help kind of get a good initial guess for the dynamic transient run. And then, of course, we started with the rigid body motion, which is the dynamic simulation part. And then moving on to the overset motion, we also, again, initialized the solution, and then we had the overset motion. We also did want to kind of see the overset rigid body motion. So essentially, you can take the overset grids and then also prescribe it with the rigid body motion, which is essentially rotating the entire domain. In terms of the solver setup, we were running at Mach 1.06, which is just a case from the TDT, and with a Reynolds number, a non-dimensional Reynolds number of 8.15 times 10 to the fifth. We ran 4 different cases, alpha 0, 10, 20, and 30. That's the free string angle of attack. We were running a Urans model. It's a Spillard RC QCR 2000, and those are just modifiers to the turbulence model. So you have your rotational and curvature model signified by the RC, and your QCR 2000 is just a non-linear modification. We initialized with 1,000 time steps, and we were targeting about 5 cycles at 500 time steps per cycle. We were running on standing bridge architecture for all the simulations, which is just the CPU architecture, to make sure that all of our simulations were receiving the same resources at 320 cores per simulation. So here's just an example of what you might see in this is just a free stream alpha of 0 degrees, and you're rotating about 0 with an amplitude of 10. So the way that we wanted to post-process this, we wanted to split up the period of oscillation into cycles based on the iterations per cycle. So as you can see, you have cycle 1, 2, 3, 4, 5, and these correspond to how the body is actually oscillating. So just looking at the moment coefficient, you can kind of see that the cycle 1 does experience a startup trauma from initialization, which is expected. It might be kind of hard to see in here, but around this area, you see that it was initialized with this startup trauma. But the rest of the cycles 2 through 5 are in very good agreement with each other. Not much to be said here, but this is the normal course. Very startup trauma down here from initialization. But we can say that cycles 2 through 5 were in very good agreement with each other as well. And then moving on to the axial force, you might notice the difference right away is that there's this double peak and double trough within one cycle. But this is simply because your axial force is a quadratic function rather than a linear. So you're essentially oscillating through this free string alpha twice. Now onto the cycle time, we just overlapped all the cycle times on top of each other. Here's that startup trauma that I was mentioning earlier. These are just your moment coefficient for your rigid body versus your overset. They're very good in agreement with each other. So now that we know that cycle 1 has that startup trauma, we can ignore it in the follow-up slides. So this is kind of where we try to isolate the dynamic contribution of the actual motion itself. We decided to remove the linear, or some might call it the static contribution. So this is your CM alpha or CN alpha term. And again, we didn't include your axial force because that is a quadratic function, so you can't really remove that linear component. Yeah, so I do want to point out that we did calculate the linear component separately for each mesh method, and they did vary by 5 times 10 to the -6 per degree, which is kind of important later on. This is just showing, this is highlighting the dynamic contribution. So as you can see over here on the left side image, this is just your moment force coefficient versus alpha. And then on the right, this is the CM, what we call CM dynamic versus alpha. And it really just highlights, the dynamic contribution. And here you can see that this is your alpha 10 scenario, and this is your alpha 0, alpha 10, alpha 20, alpha 30, and this is varying by a linear shift. And one of the most interesting things is your alpha 30 case, which we'll talk about as we get closer to the end. Same thing here with the normal force. You kind of see the same trend before. Now, this is kind of where we're getting to the bulk of the presentation of what we found most interesting, which is where we're comparing your overset method versus your rigid body motion. So they're in very good agreement. The orange line represents the rigid mesh motion, whereas the dashed blue line represents the overset motion. And then the arrows, the black arrows, indicate the rotational direction of the hysteresis loop. So for each one, they start about -6 degrees for your alpha, and then for your CM, your CM dynamic, it rotates counterclockwise, whereas your CN dynamic rotates clockwise. And then as you move further and further down in your free stream alpha, so the last case was 0 degrees, and then this case is 10 degrees, you start to notice this slight linear shift between the different methods, which is important because what I mentioned before is that your linear component does vary by a slight difference, and then also there may be some grid dependency issues since the meshes aren't one-to-one comparison. But you can still say that they're in pretty good agreement with each other. And then same case with the alpha 20 case, very good agreement. You still see that linear shift between the two methods. Now moving on to what I think is the most interesting case is the alpha 30 case. You still see that linear shift, but it's a little bit more variable. So down here versus up here, it's not differing by the same linear constant. And then you start to notice this crossing behavior at about 36, 37 degrees, where your rotation flips between the two. So you're, in the case of CM dynamic, you're moving from a counterclockwise direction to a clockwise direction. And this kind of suggests that there's some sort of dynamic instability in this scenario, because you're reaching these high angles of attack, and then so your body wants to start tipping over. And then since it is a forced oscillation case, you're prescribing this motion, you're essentially just slendering it back down into the flow. Now that we can say that the rigid mesh motion and the overset motion are in very good agreement with each other, they produce pretty close values within each other. We really wanted to calculate the computational overhead of the overset method. And this is because with overset, you're also recalculating these meshes at every single time step. So it becomes a lot longer in terms of your solver time. So in order to calculate this, we wanted to compare the computational resources, which is how much resources are you throwing at it in terms of your computational power. And then we were looking at the computational complexity of the system. So like how many grid points that you're using, and also the total iterations to solve this problem. And then going down to this table down here, this is just a sample from your Alpha 30 case. And you can see that we use 320 cores between all methods, and then the compute hours differed by about 12 hours. So that's what I was talking about with it recomputes every single time step. So your overset was obviously it had a lot longer compute hours. And then the number of grid points and total iterations. And then once you find these, what I call the CR over CC values, you can normalize the overset value by the rigid value. And then that gives you your overhead cost of about 12.2%. So this kind of quantifies the break-even point of, when would you use overset versus when would you use rigid body motion. So you can say that, you can increase your number of grid points by 12.2%, or maybe you want to increase your total iterations by 12.2%. And then that kind of tells you, hey, after this point, this is whenever I start wanting to use the overset method instead of rigid body motions. So we did have quite a bit of issues just running into just starting these simulations with FUM3D, as well as some yoga limitations that we had. Now in yoga, a hierarchy system has not been developed yet. And this is mainly because it was originally developed for rotorcraft, so it had no use. We didn't really have any use cases for something like a blunt body vehicle. So the reason for this is that you start to have this inability to have multiple background grids. So in the case of rotorcraft, you have multiple moving bodies, so you still only have one background mesh. But in our case, we wanted multiple background meshes. So as you can see in the bottom left, that this picture, we try to use 3 grids, but it would just cut through the weight, and that's because there wasn't really a hierarchy system developed. Now yoga can use more than 2 grids, but it's just in the case that we have with multiple background grids. Additionally, since we did not have this hierarchy system developed, using an incorrect grid order within yoga, it causes the far field to rotate rather than the actual inner grid, which we want to rotate. So kind of to wrap everything up, so yoga does provide a substantial gain for dynamic simulations, and there's a very good agreement between the previously known rigid body simulations as well as the overset solutions. There's only really a 12.2 overset overhead cost, and this kind of helps to reduce a lot of the computational complexity within areas of interest, such as the weight, and also being able to move parts of the weight to the front of the grid to resolve a lot of that bow shock. This also helps to minimize regridding with the new drop-in approach, kind of like I mentioned before with the vehicles, how for every single new vehicle that you want, you would have to develop a new one, a new grid, whereas in this one, you can separate that inner grid and then replace it with another grid since it's multiple grids. The initial results, they did start to show dynamic instability at high alphas, and this kind of agrees pretty well with the preliminary TDT data, although future comparisons are required once the data is actually fully extracted. Now, there were a lot of time constraints. I've only been working on this specific project for almost 12 weeks now. So there's a lot of obstacles within learning yoga. I don't think I actually got yoga to work until probably my halfway through. And so there wasn't really enough time to fully develop this workflow. And we also want to target more TDT points to actually get a fully resolved solution. And then again, like I said, TDT data has not been present yet. So future work, we do want to expand all the conditions, run more mock numbers, run different angles of attack. But we also want to look at higher fidelity models. So like I mentioned before, this is a very somewhat coarse grid. So we want to do some grid convergence studies to make sure that your solution is independent of the mesh itself, but also, having a higher computational complexity of the models. And then future work can also, we can move to scale resolving. So that's just a higher fidelity turbulence model, such as LES or DES or IDDS. So this would kind of help with a closer agreement with the experimental results of TDT. Also, applying these models to a 6-DOF model would be very advantageous. Like I mentioned before, in the ballistic range models, it's very computationally complex. So being able to use this overset method for something like a ballistic range model would help a lot. In terms of what's next for me, I'm finishing my master's in aerospace engineering at UCF. I have 1 more year left. And then after that, I plan to continue to work towards a PhD at UCF. I do plan to have my dissertation related to something EDL. And hopefully I'll see everyone here back at Langdon. Just my acknowledgement slide. Eli, he's been my mentor for 11 weeks now. So he's been helping me with everything along the way. Cameron Drewer, he developed and he created yoga. So a lot of this work would not be here without him. Mark Schonenberger. Coming into this branch, I hardly knew anything about entry, descent, and landing vehicles. So he sent me a lot of resources just in order to learn more about dynamic stability and about my project itself. I also want to thank my advisor, Dr. Michael Kinzel. He's the one who kind of put me here in the first place, and he always pushed me to learn more about everything else. And then, of course, everyone here at Langley, Monica, and all the other interns for making this experience very enjoyable. And with that, do you guys have any questions?
So when you're like using a different vehicle, so you just kind of just like drop that last layer on top. Do you have to do any refinement of the other layers, or do you think it would work pretty well?
So it really depends on your vehicle itself, but a lot of the pros with Overset is that you can scale these features. So if you have a wake that you have some unit wake or unit shoulder, and then you can just scale these values up and move them around how you see fit. So yeah.
Go to slide 20, please.
Specifically, no?
Yeah, so I guess, so that's alpha of the free stream, and then
Yes.
that's the alpha of like your rigid body rotation.
Yes.
Okay.
Yeah, it is kind of hard to see on these projectors, but yeah, that's your free stream alpha of 30 degrees. So you're oscillating about 30 from the free stream.
Okay, and then can you go back to that slide that the GIFs, the very beginning?
The mesh images.
You want this one?
No, the basic.
Oh, the basic one.
Yeah. So as somebody who has a very surface level, or I guess my experience with CFD was just in a class and it was now approaching 4 years ago, why can't you just like re-grid or re-mesh instead of just rotating your mesh? Why can't instead of, I guess I don't understand why you can't leave that yellow cone fixed in the direction of the free stream if that's what you want, and then just generate a new mesh. Is it really intensive to generate new meshes?
Yeah, so really depending on how, well, first of all, it depends on what grid generator tool you're using, because some, like Pointwise, are a little bit harder to make new grids versus held in mesh. You can make them pretty quick. But yeah, that's also one of the things is time consuming to create new grids, and that's not really something that you would want to be doing. Whereas in Overset, you can just rotate that. Yeah.
I'll add in another point to that too. If you go to the slide that has the wake contours, so yeah, with this one you can see on the rigid mesh off to either side of the wake, you've got a lot of refined grid that's really not being used for anything, and so it doesn't only drive up your need to regrid solutions, but you're wasting a lot of your computational time on every solution on an area that doesn't really have gradients that needs to be resolved. And so the overset approach allows you to kind of focus that, because with rigid mesh, on the animations, that wake is moving across the entire refined region, whereas overset keeps you within a single region. So you're only on the rigid mesh, you're only really using a sliver of your whole mesh at a given time.
So why does overset take like additional time?
That's because it is recomputing this grid, because you're rotating this grid, like in, yeah, every single time, so yeah.
So is what you're doing, you're prescribing like a motion of the vehicle as a function of time and then calculating the aerodynamics?
Yeah, so essentially you're just giving it a prescribed pitching oscillation. So you're so in this case, I think what this is a free string alpha of 30 degrees, and you're rotating with an amplitude of 10. So yeah.
Okay, so what would happen? Like, let's say your vehicle was extremely unstable. Like, let's say there's a vehicle that's like extremely unstable. So those oscillations would like grow over time and become huge. But you're using a thing that's like a stable oscillator, or some vehicle that's stable or just not really changing. Would that mean does the thing that you use as your like forced oscillation, does that have to accurately kind of represent, like come from another source that represents kind of how this vehicle would behave, so that your calculations are reasonable? Because otherwise I think it could be like some sort of like mismatch or something.
Yeah, you're just asking like if the body is naturally like unstable, and so you would obviously see this increase in instability, but since you're prescribing it a forced oscillation, right?
Yeah, if you're giving a forced oscillation where in real life the vehicle would not oscillate like that.
Yeah, so that's one of the things about this method, is that you are giving it a forced oscillation, but in something like a 6-off model, like in the ballistic range, you can like look at things like that. But yeah, in the case of this, you probably see just more instability within the CM versus alpha curves. But yeah, you are forcing it back down.
And I guess one thing to add quick, when those oscillations are prescribed, same as when they're prescribed in TDT, they're prescribed to a reduced frequency that's typically driven from a flight trajectory that's informing that.
Questions?
Jackson, this whole simulation is done steady state. Have you captured any transient effects?
Yeah, so this is all transient.
This is all transient.
Yeah,
Okay. So your initial conditions, how did you just kind of curious how you specified that? Did you specify your motion prescribed as starting at an upstroke position, or
Yeah, so depending on the free stream, so we prescribed it some free stream, and we just did a static case of that. And but yeah, the body was not rotating.
I'm asking because I'm seeing the wake sort of has as just right at the start before you press play. I see the wake kind of
Like that. Yeah. So we think a lot of this is because we're initializing with the solution, and then we have that startup trauma. So that's probably why you would see something like that. But then I think later on it just kind of balances out.
Yeah, so you're moving from transient into steady state, you think?
Pseudo steady.
Yeah. Pseudo steady to a transient state. Yeah.
And whether that's an effect of the unsteady RANS modeling or the time steps we're taking or so on, that's where the further studies would come in to kind of narrow it down.
Yeah, and then it brings me to my next question, your hysteresis loops. You've had one that counter-rotated the other one, rigid versus the overset. Is that right?
This one. Or
no, I think a little before that. It was the one right before that. You had the hysteresis loops for the pitching moment counter rotate the pitching moment for the overset grid mesh. Is that physical, or?
I believe you're talking about this one, right? If I'm not mistaken, where it flips, or
Just in case it's hard to read, it's CM on one side and CN on the other, right?
Yes. Yeah.
Okay.
Sorry.
Okay.
Yeah, I think that's the
That
confusion.
counts.
Okay. Yeah. I think the graph just got shifted over, but yeah. So one side is just your moment coefficient, and the other side is your normal force. Any other questions?
You expect the TUT to match up pretty well.
I think the trends might match up, but in terms of the actual solution, since we are running a lower fidelity model, probably not so much. And we're also using,
Makes sense.
There's a lot of active work going into answering that question beyond just this project.
some of the other meetings. Yeah. Well, I guess with that, I guess I'll end there. Thank you so
Yeah.
much. Yeah. Oh, sorry.
Okay,
Yeah.
yeah. No, I great presentation. It looks like a lot of really interesting work. I know, if I remember correctly, you started out as virtual and then came into.
Yes, correct. I started as 2 weeks early virtually.
Yeah, and so how did that go? I was just curious about the transition and hopefully the in-person.
Yeah, I mean, it started off great. I mean, obviously, just being able to start working on this project, but obviously the transition to in-person has been amazing, just with all the, seeing Langley, seeing all the tours, seeing everyone's faces, but names to faces really has been amazing.
Great, good. Thank you for supporting Eli, and Eli,
Yeah.
thanks for
Thanks for your help.
taking on the student. So, a lot of good work here.
Thank you.